Hello and welcome to 24th lecture of the course on data-enabled tribological engineering from experiment to predictive models. The lecture topic is regression and classification algorithms for tribological modeling. So we want to really learn first what are the takeaways from a previous lecture, which that was a lecture on the machine learning algorithms. What we have learned from previous lecture. You see, machine learning technique can be employed to identify relationship or models, we can use any word, that exist between input variable and corresponding output variables. This is very important for us when we have a complex mathematical equations or we don't have any relation. In both the cases, if we have a data, input and output data, we can use a machine learning to develop a simple models, simple relationship, and use those model for future prediction. So these are the important thing. Another thing which we learn is that MATLAB has a machine learning algorithm complete package. We can utilize those algorithm to choose best algorithm for our application, whichever application we are thinking about a friction loss, thinking of the wear loss, wear debris, or we are talking about some sort of lubrication mechanism, which algorithm is going to give the best solution to us based on its validation that can be utilized or can be figured out from MATLAB algorithms. Reason being very clearly that one size does not fit to all solution. That's what we are trying to say. One size will not fit to all the solution, and we may require different algorithms. We also learn that machine learning has a capability to self learn. That's what we call a self learning by observing data. So what we say, the ability to solve tribological problem by extracting knowledge from a large amount of data and improve performance by continuous learning. So these algorithms, if we really build in a manner that whatever the knowledge they keep getting, that continuously improves on, our model will be continuously improved. That will be very important. So few examples we'll take in this lecture also. I have picked up few lines from a book what we call as the MATLAB for machine learning, Sibro, which published in 2017. That is what I have picked up the line from this book. It says that process of driving models from a given data set will be known as a induction. So this is a kind of technical term I'm using utilizing here. This is the induction, which is quite opposite to deduction. If we know the formula and we are generating some values, then is a deduction. While when we have a data set and then we are developing model from data set, that will be called induction. And whole process will be known as whatever we are trying to utilize this. That's what we say, the inference refer to whole process of making prediction about new situation based on the new observation or based on the observation which has been done. So what is the overall purpose? Learn from a data, develop a relation, use that relation for the future observation if there's a need to continuously improve the model also. That is what we call a reinforced learning or reinforcement learning. That is very important, and then we should be utilizing this. Of course, we will be covering deep learning in the next lecture. That's a lecture 25th. But often people get confused because there are too many terms: deep learning, machine learning, and artificial intelligence. So that's why here I'm trying to give some sort of a detail on this. You say that deep learning is a subset of machine learning. Machine learning in turn falls a broader domain of artificial intelligence. So we can say artificial intelligence is a big domain, machine learning is subset of that, and deep learning is subset of the machine learning. And in next lecture we will be dealing with a deep learning algorithm, particularly for tribological purpose. The question comes, why we have been again and again using the machine learning Naturally, there are a number of advantages of machine learning, particularly for tribological problems. We say it helps to solve the problem. Now, when we get a data, we may figure out there are some cracks, there are somewhere debris which are really requiring alarm, or whatever we were thinking about ultra mileware, it is a mileware. So this learning can come from machine learning, and it may help to formulate the problem. Like some lubricant which were supposed to work very nicely, but data indicate the lubrication is missing some important aspect or some important attitudes, then we can formulate the problem on that. So it is very important to formulate the problem itself, or first identifying and then formulate the problem. Many times we have many number of variables, like in lecture 10th we learned something like Reynolds equation. You can see here there are a number of terms. We say that is viscosity itself is a function of temperature and time. Naturally it will be a very complicated relation. And then again this velocity in one direction, or maybe say x direction, velocity in the z direction, velocity in y direction. If we continuously utilize this, then equation will be very complex. So often we take some assumptions and we try to solve in one dimension or two dimensions. So these are already assumption, we are solving it. Naturally, when a new situation comes, it may not be a part of this, or maybe those assumptions which we made may not be correct also. So what we say many times, we solve the partial differential equation by considering some assumptions, by neglecting some variables. But after that, if again that one of the variable becomes a dominant, again we need to resolve the equation. While in the machine learning, we have a number of algorithms which figure out what are the really importance of each variables, and we can quantify that, and whichever variables are very important, then only we move in that direction. We don't solve the partial differential equations again and again, and we don't really require again complete elaborative manner to solve each and everything. Many times we don't have a relation, or something new comes, new material. We don't have rules, we don't have laws, we don't have a theory. So how do we go ahead? And most of the time we have seen in innovation, we don't have established things. So that's why this machine learning will be very important. Whenever we want to invent something, we are developing something, we want to develop into a new grease, we want to develop a new lubricant, we want to develop a new material, and most of the time the machine learning algorithms will help us a lot. Sometimes we require a customization, we want to really change only few parameters, or maybe we want to do some sort of a change in the one parameter and one setting, then again the machine learning will be very useful to us from that point of view. Now in my view, which is a major advantage, is that we are utilizing supervised learning. Now we have a data and we have exponential learning also. I've seen in industry, many people have a lot of knowledge about tribology. They have experiential learning. Oh, this grease will work, this grease will not work. This bearing will work, this bearing will not work. But they don't have a complete mathematical background. They can't solve this partial differential equations. So then there is a difference. We say when we solve the partial differential equation, people say, "Oh, you are from academia, that's why you are doing it." People use experiential knowledge, and we say, "Oh, there is no science behind that." So there is an issue, and always there is some sort of a dispute between industry and academia. So if you want a good industry academia interaction, machine learning is a very effective tool to utilize that. In fact, in my view, many time tested knowledge which person hasn't learned over the period of 20 years, 25 years, that can help even in a supervised learning in a big way. And that's why here I am defining tacit knowledge. We say tacit knowledge refers to knowledge, talent, ability gained by experience, because here experience matters a lot. Just by theory we can solve something, but experience will be a very important for us, and that machine learning helps to provide combination of theory, science and experiential learning. and overall package will be more useful for us. As earlier also mentioned, that reinforcement learning, here we come up with a feedback loop. Now, feedback loop can come through the also tacit knowledge or experiential learning. And so whatever the knowledge, we keep on improving it over the time, and then it becomes a very important for the way for the society in a big way. So what we are saying, reinforcement learning algorithm possess ability to refine model or knowledge, whichever ability you have, by adopting variation in operational conditions. Now, as I mentioned, in we have three sets. S1, people have used only temperature and pressure. S2, other person, they have a temperature and viscosity. And third relation, people may have the pressure and viscosity. And quite possible, if I use these three relation and reinforcement learning, I can connect, can develop a one common relation out of that. So it is important to connect and then develop overall to improve the model, to improve the knowledge by adopting the various data which are available in domain or in literature. Now, if I, in short, I want to say machine learning is a modeling methodology. However, many people will object on that. In my view, it is a modeling methodology that encompasses the data. Now, here I am trying to define the data. Say data refers to various form of information. It can be document, it can be graph, it can be table, it can be photographs also. An interesting thing is that how to interpret the graph, how to interpret the photograph, how to interpret the table, machine learning has algorithm for that purpose also. Or there are newer development happening in machine learning which are being utilized. CNN is very big in that way, and we'll be detailing particularly when we are talking about the deep learning lecture in the next the lecture 25th. Now, many times we talk about effectiveness, because I have seen some researcher talking of saying the machine learning is a buzzword, nothing else. We have been doing automation since 1990. What is a really machine learning? It's not really doing much. So here we want to know that how to make machine learning more effective. Particularly many theories come, but how to implement effectively, that matters a lot. It should be going widespread. It should not be restricted to few labs, only to few people. And somehow machine learning has already achieved that milestone. It has been widespread and many people are getting aware with this. And it is really crossing all the boundaries. It is utilized in almost all the fields. So that's why it will be turning out to be very important to learn. And then how it becomes effectiveness, we say machine learning is a computational methodology that encompasses process of extracting predictive models. So earlier we used to solve the equation to get a predictive models. Here we can extract from a data which have been provided, and the literature is full of the data as such. And then we say effectiveness of ML process is determined the way we are trying to utilize it. Now here we have already covered in a previous lecture that overfitting is one of the major issue. Whenever we are talking about the curve fit, we know very well that overfitting is a major issue. And then over here overfitting is already because the supervised learning is there. And how to solve that? This is important. And machine learning helps us with this. Now this is what we learn in regression. And what in this lecture we are going to emphasize more on classification. In classification, I have shown the two classes. One is a triangle class, one is a filled circle. So there are two classes. So we say C1 is a C class and C2 is the filled circle class. And then here we need to find out some sort of hyperplane which separates a triangle from a filled circles. So how do we go ahead? So this is a classification, and then we are able to show there is some sort of hyperplane which is trying to separate these surfaces. Of course, in an actual case, we will not be able to find the graph like this or figure like this. It will be mathematical. So we will not have that kind of understanding. Naturally, we will require some mathematical relations to figure out effectiveness. But here, just to visualize I'm showing some figures. This is what has been shown. Now here what are the drawbacks? We are able to see this triangle is moving and is coming in the class, maybe say in this case ICC use the word class 2, this is the class 1. So even though triangle which is not part of class 2, it is coming in the class 2. Similarly this is coming in class 2, this is coming in a class 2. It is not that effective. Now coming to the filled circle, that is coming in class 1, which is also wrong, right? So we need to have some algorithm which can really give the good results. However, there is another hyperplane which you are able to see, because of the we are able to visualize, it is making really curve in such a manner that all these are separated from each other. Now here there is no problem, but what we say, it is overfitted. It is 100% proof, but quite possible next time a new data comes something like this square. Now this square is a part of maybe this square, is it a part of the triangle, is part of the filled circle? It is not very clear. If I try to mix this line, it will be part of the filled circle. So if I go with this, that's a triangle. So it is very difficult. And then by here, as I mentioned, in the case this is C2 and C1. Now this new curve, because of the position xy coordinated has come here, it is by default is coming C1. That means there is some assumption, and that's what we call, it is going to may give a good the bad results also because of the overfitting, and we require a correction, and machine learning helps to correct that. Overfitting can be solved using a machine learning, and that's what the importance comes to the machine learning and which kind of approach and how we are trying to utilize this approach. So what we see, that just an achievement of desired goal through machine learning approach is depending on the utilization of appropriate training data, because whatever we do, we start with the training data. We have some output already known, some input known, and we try to predict the model, and model predicts the output, and we compare output which has been predicted and which has been given to us, and we try to minimize error. And overfitting comes because we are trying to minimize and almost achieving 99% results, but next data, future data which is coming, will not be knowing already the model in the hand, and when prediction comes, it may commit an error. So we say that it is basically based on the training data, how we are giving a training. Of course curve fit also comes in that way, it gives a training. Hence it is imperative to machine learning methodology to acquire impartial training. We say that we should have training data which are really attributing to the real world data. So these are the just words. What is the real world data? We don't know. But what we can understand, that and the real data many times come with some noise, and if noise makes some sort of a problem in the training data, we will be landing to the wrong solution. How to filter out the complete noise using machine learning, it's important for us. So what we say, the phenomena of achieving consistent model, which is again and again can be repeated, it can be known as a, this process will be known as a generalization. So in short, I can say effectiveness of machine learning depends on extent to which generalization is efficiently or effectively achieved. So this is way, if we are able to achieve generalization, and really that model whatever we created can be utilized for wider situation, that's a generalization, and it will be the our aim. So what we say, start with the generalization. We are saying here the training data which are what we are getting, we generally assume they are correct, whatever the data. Now tomorrow if I am picking up the data from a tribology handbook, I will assume initially is correct, but there may be a lot of noise also. A person who has utilized and got a friction data or temperature data or pressure data, maybe the sensor was having some sort of noise. So whatever data we are getting, it is already noise. So how do we rectify, how do we correct that? So what assumption initially, the assuming the training data is correct and well aligned with the model results, maybe it treated as a overfitting. Certain outliers which are having a high noise. Sometimes they are outliers, maybe not coming very near to the right solution. They penetrate because of the outliers. They penetrate in region which is not belonging to their region. They cross borders occupied by other classes and disturb established boundaries itself. And in this situation, generalization fails. So what we are trying to say here, if training is not proper, if training is done with a noisy data, then problems will be there, and we required some sort of solution for that. And as we say, concept of validation is introduced to address this issue. That means if there is a validation step, then this noise removal is possible. What is a validation technique? Uh, it really reserves some portion of the training data to examine and evaluate or monitor the performance. So what we say, during training phase, validation set is not used. So suppose we have 100 data initially given, we may use 80 data for the training purpose. Remaining 20 data we will keep only for validation purpose. And these data, they have not seen the model at all, and they are not helping at all to and then they justify model. But validation time, they are trying to figure out whether model is accurate or not. If it is not, it will give a feedback, and that's why we say validation provides a kind of feedback, and we can improve our model. So what we say, during training phase, validation test is not been utilized. Use validation set to evaluate model to assess the presence of overfitting. If there is overfitting, then it should be pointed out, because modeling error of the training data does not provide any indicator, because when you are trying to model it, it doesn't give. So the validation been utilized. Now validation also can go in a number of ways. We say when model's performance on the validation set is much lower, if the performance we check and we find that the model is not giving right results, then we say results unnecessary, the model is unnecessary, overfitted or underfitted, whatever you say, and we need to tweak the model. How to tweak a model? Again, there is an algorithm to tweak the model to remove this problem of overfitting. Now there are various methods. So here what we are saying, 80 training set, and then the 100 models, 100 total data, 80 for training set, 20 for validation, and that has been shown. This is the total 100, 80 give for the training purpose and 20 for the validation. That's a one method. Now second comes that maybe you think about 70% training, and then instead of the validating can be divided in two part, we say 20% for testing and 10% evaluation. So whatever we are trying to give the feedback loop in the training, we will find the model. In testing phase, that model will be evaluated and the error will be found. If there is no error in this, then even it can go to final mode of evaluation purpose also. So instead of one the validation, it will be the two checks also, and then it can be much more robust. And in case of the third one, we say the training, testing, evaluating, and improvement. We are here assuming we don't have enough data, and reinforcement is essential for that. Our model need improvement or continuous improvement. So this also possible. So this is a two-step, this is a three-step, and this is a four-step process. Any of the process can be utilized for the generalization purpose. Naturally, when you are going for more and more steps, generalization will be better and better, and it will give the better results to us. Now, how to achieve generalization? That's what I have picked up this line, this example from book Phil Kim 2017, which is the MATLAB deep learning book. And then here he has shown also training, this is the total 10 the blocks. Training set contains 8 blocks, validation contains 2 blocks, and what he says that training data partition into the training set and validation set. So training data, of course these data will train, but we have a separate form to set for the modeling purpose to come up with the predictive model, and this is a validation set only, and they have given the ratio 8 to 2. As I say, that can be 7 to 3 also, depends on the algorithm which we are trying to utilize. We say the model should be trained using training set, and performance of the model will be assessed by utilizing the validation set. The same thing. Now, once model demonstrates satisfactory performance, proceed to conclude training. That means model is there, then one can go directly to the next level. If performance fail to yield a satisfactory results, this is interesting. If it fails, then there is a noise in the data. How do we filter out? So we say it is recommended to adjust model by changing a training set and validation set. So initially this is a complete training data, and then we utilize this for the training purpose and this for validation purpose. So we will change it. How do we change it? There are a number of methods. We say initially maybe you can think about the first block and second block for validation, then maybe say fourth and fifth block for the validation, then maybe say the fourth block and ninth block for validation, and we continuously iterate. So the noise comes down to minimum level. So this is very important for us. So what we say here, instead of maintaining first separated set, cross validation involves the repeating process of dividing data. Cross validation is a technique. This is what we call a cross validation. And in the last lecture, when I use a MATLAB and I mentioned that they are going to have with a 5-fold cross validation. So this is the same thing which we can go for the cross validation. Cross validation is a technique that preserves the unpredictability of the validation data, hence enhancing ability to identify overfitting. Validation data represented by this is a dark color, dark hue, is randomly selected. So we need to have the necessary steps in the algorithm to correct it, and then do an iteration so that overall results are in our favor. Just to illustrate what I mentioned in previous slide, again I am taking example of previous lecture, that lecture 23. This was already shown as a linear regression model, and then we use some hypothesis. We did the cost function also, and then we utilize a gradient descent algorithm to improve the theta value. Initially we assume theta is 0 0 0, and then at every iteration it has improved, and this is a learning in the rate. We can change the learning rate alpha something like a 0.01, 0.001. Of course number of iteration will change, or 0.1, depends. Now we need to be checked on that, and this is the cost function has been the gradient has been given in this form. We showed a number of algorithm that time. We say that MATLAB has a tree regression analysis of 2 types, SVM, and then you can use another thing also. And then we try to show that even in many places literature say SVM is a good results, but somehow in this case the result was a linear regression was giving the better results. And it was mentioned that compare validation finding and select the most suitable model for a given regression problem. So this was important for us. And then PCA is also when we talk about the how do we really extract the feature or relevant feature or more important feature, that's also possible using this MATLAB algorithm. However, we say that you can follow the MATLAB, but sometimes we require our understanding, because the MATLAB may provide a program, it may give a kind of the black box. We are giving something and something is coming out. So once you develop your own couple of programs, and then after that you go to the MATLAB, it will be always advantageous to understand how the MATLAB is trying to solve the problems. So utilize and thinking from that angle, I am just trying to show one algorithm which we have developed for the linear regression. Of course, it's very complicated, or maybe and when we are not able to show in complete manner. So here what we are saying here, that here the training set has been taken as a 70%, and 30% has been kept for the validation purpose. Another important thing which we realize is a convergence limit. Here we have kept n is to minus 10 as a convergence limit, because we are when you are iterating and we are trying to calculate a RMSE, then if it is a lower limit on the n is to minus 10, the results are far better compared to the keeping a lower limit. However, I am going to show the both the features. So this is the data which has been mentioned, and then after keeping it n is to minus 10, and we find that training set and testing set, First training set, of course, in the first iteration, always it really gives a good results. Quite possible it may not give every time. And in this case, training set has a RMSE value as a 1.0133. Testing has a far better, and same thing in MSc. And we also mentioned that RMSE is far more accurate to compare among the different algorithms. And you can see this is a cost function is almost zero. That's what we are trying to say, 10 is to minus 10, and then the comparison. And this is what the linear regression model has been shown here. And here the how the error is really decreasing, and it shows that within 6,000 iteration it has come to the real low level as such. Initially it is almost zero point 0.5 and it comes to the 0.000 something, and after 6 iteration. Now we want to really know how the learning rate is affecting it, even though we have kept conversion limit as a 10 is to minus 10. You can see here the alpha convergence rate is a 0.01, second case has been shown as a 0.01, and third case a 0.1. And we are able to see in when we are keeping learning rate as a 0.1, we don't get any data as such, or maybe say and that we get a overshooting, and then this weights are not getting updated, it can keep oscillating, so there's no convergence, and maximum number of iteration passes and nothing comes out in as such. There's a highly unstable solution, or instability in convergence occurs in because of this reason. However, in the first case 0.001, we are able to see accuracy training set as well as testing set. And zero point 0.1 also we are able to see. This doesn't this also indicates that not necessary that accuracy improves with a reducing the alpha rate, because number of iterations are matter also. In this case, number of iteration naturally will at least be 10 times more compared to the second case. So we need to keep changing and then see the results which are really favorable, or maybe it is giving fast convergence to us. Now in this case we have kept learning rate as a alpha 0.01, but we are keeping the changing the convergence limit 10 is to minus 6, 10 is to minus 8, 10 is to minus 10, and this was what we say best results. Now here we are able to see that RMSE value is 0.48 something. Here it has come down to 1/10 of that. So this convergence limit itself has a lot of importance. So sometime in MATLAB we have a possibility that we can go with the convergence limit as infinity, and almost zero. We can do that also. While coming in the further improving this one, we are getting good results. So when we develop our own algorithm, we are able to play with this kind of parameters, and we are getting better feeling whether the results are proper or not. So this was what I mentioned about the regression analysis. Now there's another one method known as a logistic regression. Now here I want to clarify it. Even though the name is a regression, but it is a classification. So machine learning has utilized a regression, logistic regression, but from starting itself it has been used for to classify it, even though it is a part of the supervised machine learning. And logistic regression generally belongs to the this kind of, we say that it's a two class scenario. What are the two class scenario? Something like a failure or no failure is a one, fault or no fault, crack or no crack, and oxidation no oxidation, something like the female male 1 0. And so these are the two class scenario, and then they either say yes or no, go or no go kind of thing. So what we can say, in contrast to conventional linear regression, logistic regression is suitable for purpose of modeling binary variable. So it gives the response variable as a binary variable, and it takes only two values, something 1 and 0. Now 1 can be anything, 0 can be anything. In this case maybe I can use a 1 for the male, 0 for the female, or reverse also. I can use a female 1 and a male 0. It's possible. By utilizing one or more additional variable, now I can choose anything. I can think about the weight, I can think about the height, I can think about the crack size, I can think about the wear debris as a predators. So this can be done to classify. Earlier algorithm we say regression. Second, logistic regression, even though name says regression, but it's the classification, it's not a regression. Now, just to understand in slightly different manner, we are taking example. Here you can see the gender and height. Now, they have calculated the female height, which is they are showing is a lesser than 170 centimeter, and male height in case they are showing always maybe say around 166, 167 to 185 centimeter. That is what that data has been mentioned. Now, major question comes, how do I go with the linear regression? How will I fit it? It's not fitting at all. So what we say, variable x in this case indicates individual height, that's the height has been mentioned here, where y variable denotes individual sex, value 0 indicates a female and 1 indicates a male. Simple regression or linear regression is not suitable for this scenario. So that's why we require a logistic regression for this purpose. Now, particularly for logistic model, what we really required, we required one mathematical model to be implemented which really can suit it. We required some sort of a coefficients to be interpreted based on the training set, and then finally evaluation. So training, the way we mentioned, and validation, same thing can be applied on this. And then whatever the model we choose, we need to think that it is really our the logistic model will choose, it really fits in this binary case, like either it should give 0 value or it should give a 1 value. However, there is another when we are talking about classification, one good algorithm is a naive Bayes algorithm, what we call it is a generative classifier. Generative classifier is basically, it requires more parameter to understand. It will try to understand whole class and interpretation in better manner. While logistic regression, which we are trying to cover in that, is a discriminative classifier. And what's the difference? We say discriminative classifier focuses simply on learning to distinguish between the classes. All these two classes are different without gaining significant knowledge. So it has only one or two information, that's more than sufficient. It will not go in a multivariate analysis. With the naive Bayes can be utilized, again these algorithms are available in most of the softwares, we can be utilized. We have utilized, and maybe I'll cover in this lecture, we have applied on to separate the wear debris, and we can think about that also. Now here, that's why we are showing here that different wear debris. You can see even the fatigue debris, there is some difference in the features. Rubbing debris, there are features. Severe debris, again there are two example are being given. Cutting, again the two example have been given. Fatigue, again one more has been given in this case. Cutting, again is more has been more example has been given. So this we really require data from SEM image, and these data are converted. So that means we take image, we uh, change image to the data, and then you apply a classifier algorithm to classify whether, if there is a wear debris, we collect it, where we need to figure out whether it's a cutting wear, whether it's a fatigue wear, is a rubbing wear, is a severe wear. We can classify based on that, but it is not a binary, it's not a 1 or 0, it has a more number of classes. Now coming back to the logistic regression, as we said, we really required a function, and if you look at this S-shaped function, which is known as a logistic function or sigmoid function, it can be given in the relation gz as a function of the z in this manner, and this is applicable from minus infinity to plus infinity. Now, what are the properties of this logistic function? I'm referring on the notes of on the Dr. Chen, which I picked up from their slide. Dr. Chen has written very clear that gz has to vary from 0 to 1. Of course, 0 is also not there, 1 is not there, and then mean values need to be selected as a 0.5. We know the z, when it is approaching to minus infinity, gz will be 0. When z is approaching to plus infinity, gz will be 1. This is the gradient of that can be given this relation, and is important. Now when we come back to the our own initial one, z can be given in terms of combination, that means theta 0 plus theta 1 x. This is the same thing which we have selected in a linear regression. Now here the model is changing. But initial hypothesis, whatever we assume that theta as a function of, or maybe instead of y, in the can be given in this relation, that we are keeping a same here. So what we say here, theta 0 is a location parameter, theta 1 is a scale parameter which need to be multiplied with x. Now one more difference comes, the loss function. In regression analysis, the linear regression analysis, we use this as square term to figure out and solve for the goodness of fit. And here we are trying to give more penalty compared to square form. We say imposition of significantly greater penalty in the case is to be applied, because we require either 0 or 1. We don't have many continuous thing in between, right? So that's why in this case we really required actual the heavy penalty compared to what we have given earlier, the square penalty in case. So what we say here, optimum value of theta is to be found by minimizing this function, this or maybe improved function. Now if I try to see in a holistic manner, what say logistic regression is basically classification, and in this case outcomes will come, but it will be having a discrete value 0 or 1, or maybe if we are going for multi classes, then it will be some different. Now in this case, particularly for the logistic regression is on binary classification, which having value 0 to 1. Now I can apply to number of cases. However, we can take an example of the health monitoring of gearbox. So I can say that where debris is coming, the gearbox is going to fail, or where debris is not coming, where there is healthy condition. And there are many parameters, but elementary level, initial level, we can choose anything. So here what we are saying, that features attribute to the gearbox, from the outcome comes binary class as 0, we can say here it is a healthy, and 1 as a faulty, depends what is the our input and output. What will be the input in this case? We are trying to give a sensor data. Now sensor data can be pH sensor, it can be wear debris sensor, it can be accelerometer vibration data, it can be anything. And then based on whatever the what will be the pH value, whatever the wear sensor the debris value, what will be the vibration level, we develop algorithm, and then we can say whether the gear is faulty or healthy. However, as I say, that this is a gross one, it is not really going in meticulously in detail. Now what is the function has been mentioned as theta, in this case has been in the terms of the product of the dot product of the theta and x. That's what we are showing here. You can see here theta 0 is basically bias, and then the theta j is in case of weight factor, and we need to find out the bias, and we need to find out weight factor. When we go for the training, we need to do iterations on that. And then we generally take values if the any times this g z is greater than 0.5, we say it is equal to 1. We don't go through this kind of thing. So that means either it goes something goes like this, and then comes to 0. So this is what a prediction and algorithm will be written that manner, and we use a conditional probability case. In this case, we say if it is a y is equal to 1, naturally other things will not be there, and y is equal to 0, it will be 1 minus this. So when y is equal to 1, probability is s theta, and when y is equal to 0, it will be 1 minus s theta. Now if I try to combine these two in conditional probability point of view, we say and the py can be given as in terms of s theta and 1 minus s theta. Here y can be 1 or 0, 1 minus y can be anything, either 0 or 1. So naturally when y is equal to 1, this will be 0, so this will be only existing. When y is equal to 0, this will be 1, and this will be only existing. So this can be given in this form. And then now we are talking about the loss function. Loss function can be represented. However, it has been, as I mentioned, we need to give more penalty, more severe penalty compared to the square form. So that's why we take a log of that in the function, and this log function is given in this form. This is what logistic regression is done. Now how to evaluate the performance of logistic regression? We say model evaluation matrix. Basically we talk about the confusion matrix. And what is a confusion matrix? It gives a table form and they really mention about 4 parameters, whether something like a we predictive negative, predictive positive, and actual negative and actual positive. Now because we need to go ahead with the classification, now either in this case particularly we say that whether the filled circle or hollow circle or the empty circle. So probability the filled circle has been shown in this domain, and then there is some sort of boundary has been shown over here. So all the filled circle are in the left hand side, while all the empty circles are on this side. So this gives the accuracy 100%. Now what is the meaning of that? When we are making a model, and then if it is a real negative and predicted negative is also there, that means accuracy is very good. Similarly, if it is actual positive and predictive positive, again accuracy is very good. Now here it was a negative, but we predicted as a positive, so it is inaccuracy. While here in the actual case was actual positive, but we predicted a negative, so again there is inaccuracy. So this is lesser will be better, this lesser will be better, a higher value of this will be more and more important, and that's why we say that we evaluate on this classification algorithm using the confusion matrix, and that's being tabulated actual versus predictive classification to evaluate the model performance. And we use 4 terms. This is actual negative, we say the false negative, true negative, false negative, and the true positive. Now what are the parameters? We say accuracy is the one, precision, sensitivity or recall, F1 is scores also. Now when we talk about the accuracy, what is a true positive and true negative? That's what is a true negative and true positive. These are the what we really require. This is the required, and overall total number which we predicted. So this is accuracy formula. When we say 100% accuracy, that means what is the meaning of that? Fp is 0 in this case, and Fn is also 0. So false negative, false positive are both are 0, and we want this kind of solution. That's what we are showing here 100%. Now coming to the precision, is a true positive divided by the true positive and false positive, that inaccuracy will be there. That much. Coming to the sensitivity point of view, and in this case true positive is the same, only thing is that here instead of false positive is a false negative, that sensitivity towards the negative has been mentioned. Finally comes to the F1 score, which is a harmonic combination of precision and recall. So these 4 parameters also been defined, and then will be utilized for the model evaluation, or will be called as how to evaluate classification algorithm. It can be any algorithms can be utilized for this. Now so we wrote also code for the logistic regression. You can see we generated some sort of random samples, and then the training has been given, initialization has been done, and then we are defining function, we are defining what is a hypothesis and what should be the accuracy also. And then if you want more solution, and of course this and then the website provides 2 good solution. If you type even the MATLAB example 4 on a Google, and you will find this exercise. So they have given complete MATLAB code also available online, and they have given 2 examples to solve that also. Now using those examples which they have given, I try to solve it, and we try to find out initially how that affects the and how the validity or accuracy is being affected by this tolerances also, or maybe say whatever the accuracy limit we are trying to give. So here we have given tolerance to function 10⁻⁻⁶, tolerance to x value 10⁻⁻⁶, and of course this is not been given in that those 2 examples which has been published by the author. However, we have tried our own. So what we are finding here, the accuracy is 84% when we are coming to the this accuracy the limit of the 10⁻⁻⁶. Now if this is increased to 10⁻⁻⁷, we are getting accuracy of something like 88%, and when we are changing this tolerance to 10⁻⁻⁸, we are getting accuracy 96%. So many times in algorithm people write our algorithm is better, Somewhat I find it may not be right way. Reason being, when you're just changing the only accuracy, convergence, how when the solution should get converged. So we, instead of 10 is to minus 6, I'm changing the 10 is to minus 7. I'm jumping from 84 to 88%. When 10 is to minus 7 to 10 is to minus 8, we are getting 96% accuracy. Again, all this has been because in this case data has been generated randomly, then every time number will be different, data will be different, and accuracy will be different also. So when we really implement, we need to think carefully. Somebody says I am getting 99% accuracy, you can see that again regenerate or rerun the program. The 99% may turn out to be 100%, or may turn out to be 95%. So accuracy as such is not that important. Of course, just to stabilize the algorithm, or we get a consistent results, we should really justify the values. What should be the limit? 10 is to minus 8 has been shown in this case, because the data which have been generated having sufficient higher value. If further value is reduced, then I have to go ahead with the more and more. Yes, so many times we say instead of going with this value, we can go ahead the 0.01% accuracy of the value. As such, we can give in that term of 0.001% accuracy. On the 0.001% of the value, and I'm using the word not accuracy, such value, so for the convergence. If the coefficient of friction suppose is given as a 0.2, maybe say 0.25. Now when I want to go with the convergence limit, I can say converge it till I get a repeated results of 0.001%. Actually 0.25 will be multiplied with 0.001 divided by 100, and that accuracy will be keeping as a tolerance limit. If that is case, then we can get a good solution. Now here, of course, as I say, the two algorithm has been mentioned by that website. So they have compared logistic regression with the LDA, and another one is the nearest prototype classification. Nearest prototype classification is known as a KNN, also is one of the classification algorithms. And then we are able to see the blue color logistic and the green color, they are coming very closer to each other, but red color is far away. Now, which one is better, which one is not better, and we can visualize it. But once we have those four parameters, then we can really compare better manner. Yes. Now, if I try to summarize the logistic regression, we say we need to do initialization. Whatever the model we are choosing, it can be theta 0, theta 1. We need to think about learning rate, and then we many times we need to set a number of iterations. As I say, then MATLAB has a infinity as a one of the possibility. We need to define what is a sigmoid function. We need to define also what will be the cost function. As I in this case, I say we need to give more penalty, particularly in logistic regression, higher penalty. So we'll take in terms of the log. This has been mentioned, shown here. Y, what is the function into log x, 1 minus y into log x. And then we know the y is generally in a range of 0 to, will be either 0 or 1. We can use a gradient descent method or some other optimization method. Here in optimization point of view, we use a gradient descent method. Then again the training, we can do training or validation, as I already mentioned, that validation also can be done, and we can go ahead with the validation separate, that means training 80% and validation 20% data. Those things can be done also, and just we need to do this to avoid the overfitting. Overfitting also will occur in a logistic regression, and then we need to apply those. And whenever we finally come up with the model or come up with the zz function, then it can be going, and then we can we say utilize for the future prediction. And I'm just going to demonstrate in the next slide, and then this algorithm results which we have done. Initially you train it, and then if it is not really giving reliable results, then you train, and you can divide the training data into the training set and the validation set, and maybe either do in the next iteration, you continuously improve. and then if you have more different kind of where debris coming out, then results may be also different. So here we applied a naive-bayes algorithm for the wear debris analysis. You can see this is the same slide which I had shown in the slide number 14, and then when we have tabulated, this is the confusion matrix. We are talking about the cutting debris, spherical debris, fatigue debris, sliding debris, and rubbing debris, and this is a square matrix, so it is a 5 into 5, right? And here what we are saying, we got a 19 particularly when we are training, we got a 19 sample of the cutting, we got a same results. 22 sample of the spherical, we got a 22 side right results. However, for fatigue case we did not get a right results, and then there are some wrong results. Sliding case also we got some wrong results, so this is important. And however, for rubbing again we are getting good results as such. So overall accuracy, if you point, number of samples which we have taken is for something like 101, and what are the right results? 19 is right, 22 is right, 18 is right, 15 is right, 23 is right. This summation comes to 97. So overall accuracy is a 0.9603, and percentage 96% accuracy. Now coming to the precision, we say the cutting we are getting 100% precision, spherical we are getting 100% precision, rubbing also we are getting 100% precision, but fatigue we are not getting precision. Reason being, here we got one data of sliding case, so it is 18 by 19. Coming to the sliding case, we got we the divided sliding, in one case of the fatigue, another case is a rubbing case, so it is a 15 divided by 15 plus 3. So precision of the sliding is bad, we need require little more understanding, and then if there's a need to, we really need to polish that understanding with the addition more and more features. And coming to the sensitivity point of view, we got the recall a sensitivity. Recall for fatigue is again 18 divided by 20, the sliding again 15 by 16. Here rubbing is what we has divided 23 by 24, while cutting and spherical are fine, and then there's no such issue. And it's also been shown that mostly spherical balls are easy to identify, and cutting, because of the aspect ratios, are easy to identify compared to the fatigue, rubbing, and then they have some sort of similarity, some sort of overlapping feature. So that's why we require we get a lesser accuracy, and then the lesser sensitivity as such. So if I try to find out the overall model precision, it comes out to be 1 plus 1 plus 0.9474, 0.833 plus 1 divided by 5 is something like a 0.9561, and recall accuracy comes something like 0.9592. And then if I go ahead, the F1 score, because many times the people say accuracy or F1 score, if we calculate F1 score, it comes out to be something like a 0.9576. So this is a way we try to get accuracy or F1 score of the classification. As I mentioned, regression we required RMSE, while coming to classification we required F1 score or accuracy that can be utilized in a purpose. With this I say thank you for attending this lecture. Thank you.